So magnetism due to spin angular momentum was proposed in 1925 by Goodsmith and Uhlenbeck to explain the splitting of spectral lines. Okay, remember when we talked about the Z-man effect, the spectral lines. Okay, you can explain the splitting of spectral lines as being due to the interaction of the external magnetic field with the magnetism of the atoms themselves. Well, okay, if you were just to rely on what we had prior to today, okay, what we discussed, okay, you won't be able to fully explain the splitting of the spectral lines. You have to take into account, in a lot of cases, in most cases, you're going to have to take into account the existence of spin to be able to explain the Z-man effect. Okay. Now, Paul Dirac derived the existence of spin using relativistic quantum mechanics, but we're not going to go into that. As far as we're concerned, if we're just doing plain quantum mechanics without combining it with relativity, we're just going to have to postulate that there's this thing called spin. Okay. And so this is a postulate that we have to assume in non-relativistic quantum mechanics. Now, since there is no classical analog for spin, you cannot, the spin operators, there's no way you can write it in terms of x, y, and z. Okay. So we say whatever these operators are, they depend on a coordinate which we're going to call the spin coordinate, whatever that is. Okay. So how are we going to find eigenfunctions, eigenvalues for these operators? Well, we postulate that these operators behave like angular momentum operators. And so we say that the spin angular momentum vector S, okay, for that particular vector, for that particular property, spin angular momentum vector, we are going to postulate that the corresponding quantum mechanical operators behave just like the orbital angular momentum vectors. So we're going to say that S squared is going to commute with SZ. So in other words, we're going to postulate that S squared is going to commute with every one of its components. So S squared SZ, that commutator is going to be 0. It's going to commute with SY. And it's going to commute with SX. Just like L squared commutes with LX, it commutes with LY, and it commutes with LZ. SX. Okay? So we're going to make that assumption. And we're also going to assume that the components of your your spin angular momentum vector do not commute with each other. So XX, SX, and SY do not commute. So just like LX and LY do not commute, we're going to say they don't, and we're going to say this is equal to IH bar times SZ. So the commutator of SX and SY is just IH bar SZ, and you can, so basically the same commutation rules that apply to angular momentum, we're going to apply that to, we're going to assume that they apply to the spin angular momentum vectors, the operators for the spin vectors. Okay? All right. And so if you did that, even if you did not know the actual expression for S squared and SZ and SX and SY, you'd be able to prove that S squared operating on an eigenfunction F will give you back S times S plus 1 times H bar squared. So S squared operating on its eigenfunction will give you back S plus 1, H bar squared, and the original function. So your eigenvalues are S times S plus 1, H bar squared. Okay? Where the quantum number S can be an integer or a half integer. So it can either be 1, half, 1, it can be 0, it can be 3 halves, it can be, what's the next number? 4 halves is 2, and then 5 halves. So it can be any half integer. And it's characteristic of a particle. Just like each particle has its own mass, each particle has its own spin quantum number S. In the case of the electron, okay, the spin quantum number S is 1/2. For an electron, S is always 1/2. Any electron, the spin quantum number S is 1/2. Now, particles that have half-integer spins, like electrons, they're called fermions. Okay, so an example, an electron has a spin of 1/2. The proton has a spin of 1/2. It's the spin of the proton that you take advantage of when you do NMR in organic chemistry. Okay, it's proton magnetic resonance. When you do an NMR spectrum, you're probing the spin of the proton in your organic molecules. The different environments of the protons will give you different behaviors for the spin for the protons. Okay. The neutron also has a half-integer spin. Okay, 1/2. Nuclei, an entire nucleus that has an odd mass number, will also have a half-integer spin. So a carbon-13 nucleus, there's 13 particles in the nucleus of carbon-13. How many? What are those particles in the nucleus of carbon-13? How many protons in carbon-13? 6 protons, 7 neutrons. Altogether, that entire nucleus has a spin quantum number of 1/2. Okay? Boron-11 has a spin quantum number of 3/2. So these things you can just look up. I don't expect you to memorize these things, but oxygen-17, spin quantum number of 5/2. How do we know what these numbers are in the first place? Well, you have to basically figure it out from experimental data. Okay, find the value of the spin quantum number that would allow you to explain whatever experimental data you need to explain that's related to the magnetic behavior of atoms. Okay. Now, particles that have an integer spin quantum number are called bosons. Okay, named after Bose, who's been in the news recently, the Higgs boson. Yeah. Okay. And so photons, light particles, particles of light, spin quantum number is 1. Nuclei that have an even mass number, like deuterium, okay, a hydrogen nucleus that has a proton and a neutron. Nitrogen-14 nucleus has a spin quantum number of 1. Boron-10 has a spin quantum number of 3. Okay. Now, for nuclei, oftentimes we use the letter I for the spin quantum number instead of S. Most of the time, we just use S for electrons or individual particles like a proton. Okay. All right. So we can show then that the allowed values of the S squared vector is just going to be equal to S times S plus 1 times H bar squared. And the allowed values of the Z component of the spin vector is M sub S H bar. Okay? And so you got another quantum number here, M sub S. And M sub S is restricted to values ranging from negative S to positive S in steps of 1. Okay. So for an electron, what's S? What did we say S was? 1/2. What's the allowed value of the spin, magnitude of the spin angular momentum of an electron? What's the allowed value of S squared? 1/2 times 1/2 plus 1 times H bar squared, right? Those are the allowed values of S squared. And so what does that give you? One half plus 3 times 3/2. That's 3/4, right? 3/4 H bar squared. So what's the allowed value for the spin angular momentum itself, the vector? Squared of 3 over 2 H bar. So that's the magnitude of the spin angular momentum of an electron. Okay, any electron. What would be the Z component? So if S, quantum number S is 1/2 for an electron, what are the possible values for M sub S? negative 1/2 all the way to positive 1/2 in steps of 1. So there's only two values. Okay? And that's what we said earlier. Electrons can either be spin up or spin down. So you can call this the spin up or the alpha spin. And m sub s negative 1/2 corresponds to a state which we would call a spin down state, or you can call it the beta spin. Okay? So the m sub s quantum number for an electron is either plus 1/2 or negative 1/2. The s quantum number, so there's really 5 quantum numbers for an electron in a hydrogen atom. N, L, M, S, and m sub s. But since s is always 1/2, we usually just skip the s. We just say N, L, M, and m sub s, 4 quantum numbers. Okay? So here's a question. How many eigenfunctions then does the s squared operator have for an electron? What are the two possible s and m sub s for an electron? 1/2, 1/2, or 1/2 negative 1/2. So it has two eigenfunctions. So we call this the alpha eigenfunction, and we call this the beta eigenfunction. Alpha would be spin up, and beta would be spin down. Okay? What are the allowed values? We just did that earlier. What were they? S squared operating on alpha would give you what? 1/2. 1/2 plus 1 h bar squared. This should be s squared. H bar squared times alpha. Right? This is the eigenvalue of s squared, which is 3/4 of h bar squared. Okay. What's sz? The z component of the spin angular momentum for the alpha spin, for alpha state? Positive 1/2 h bar. M sub s h bar. Okay. Times alpha. If I were to ask you what happens if you apply s squared on the beta state, that's going to be s times s plus 1 h bar squared times beta, right? And what is our s? It's still 1/2. 1/2. 1/2 plus 1 h bar squared times beta. So that's 3/4 h bar squared beta. So both alpha and beta spin have the same magnitude. They just have different orientations. One's pointing in the positive z direction upward, and the other one is pointing downward. Okay, so if we did the vector representation for the vector for these, what would you get? Here's your z-axis. Okay, where's the alpha spin going to be pointing at? If this is your s vector, what's the magnitude of this? Square root of 3 over 2 h bar. So that's the length of that vector. And what's the component along the z-axis? M sub s h bar. 1/2 h bar. Okay, so this is your this is the vector for your alpha spin, for your alpha state. Okay, for your beta state, what would the vector, and what else do we know about this? Only the z-axis component is well defined, so it's precessing around in a cone of uncertainty, right? What about your beta spin, beta state? It's going to be pointing downward. Magnitude would be square root of 3 over 2 h bar, same length, but your z component is going to be negative 1/2 h bar. And again, this thing we say is going to be precessing around a cone of uncertainty. Okay, you should be able to figure out what that angle is. What would that angle be? What angle does the spin vector form with the z-axis if it's spin alpha? You've got your adjacent over hypotenuse is cosine theta, right? Cosine theta is 1/2 h bar. The hypotenuse is that's the adjacent side, divided by the hypotenuse, which is square root of 3 over 2 h bar. So that's going to give you 1 over square root of 3. So what's theta if cosine theta is 1 over square root of 3? You can figure it out. The special triangle is 1, 2, square root of 3, right? But 2 is the hypotenuse, not the square root of 3. This time it's 1 over square root of 3 is the hypotenuse. This is not, I don't think this is a 30, 60, 90 angle.